are doing g of n plus h of n, right? Where g of n is the cost that you pay to reach to this state from the start state, and h of n is the cost that you will pay to reach to goal state from the nth state, right? Now we want to start with the a, we want to start here with a, so we put a in the frontier as we did, right? Now what are the children of a? What are the children of a? So children of a is c, d and e. So we picked each of the children of a, which are c, d and e, right? Now what are the f values of c, d and e? So the f value of c is, it is g of c, which is 2, right? This is the g of c, 2, and its h value is 1. So the f value of c becomes 2 plus 1, which is 3, right? The f value of d is similarly, f value of d is 1 plus 1, which you can see from here, that is g of n plus h of n, and the f value of e is 3 plus 0, which is 3. So we have c with the f value 3, g with the f value 2, e with the f value 3, right? So we add them to the frontier, which I did here, a d, which I added here, d with the cost of 2, c with the cost of 3, and e with the cost of 3, and I have moved a to the explode set because we have already explored a, right? It is clear till here or not? Is this clear till this point? Okay, right? So you have seen c, d and e. Now what is the next step? That we pick the node with the least f value, which in our case is d with the cost of 2, right? Oh shit. Uh, why is this happening? Okay, okay, sorry, I just dropped for a minute. Yeah, I just dropped for a minute and now I'm back. I hope I'm audible now. Okay, okay, yes. So what we do here now? So we have d with the cost of 2, and we pick that d, and we see the childrens of d. So what are the childrens of d? So the childrens of d are g and h, g and h. And what are the f values of g? So f value of g is 1 plus 1 plus 0, which is 2, and f value of h is 1 plus 3 plus 0, which is 4, right? So in our frontier, how our frontier looks like now? So we have g with the cost of 2, and there was already c with the cost of 3, e with the cost of 3, and this child of d, which is h, with the cost of 4. Now, what we pick as the node to explore, we pick the one with the least f value, which is g with the cost of 2, and we check whether is this the goal. We see yes, this is the goal, and we return it. So we did find an optimal goal g with the cost of 2, and yes, uh, and we just return it, right? So is it clear now? Okay, okay, nice, perfect. So just stop sharing this, and I will present the, and, okay. So now we saw this example, right? So this just explained a star. So what if there are some memory problems? So similar to this IDDFS, iterative deepening depth first search, we can also have iterative deepening A stars, where you do DFS but prune when the cost is greater than current bound, and you increase the bound. Another thing that you can do is you can try depth first, branch and bound, which essentially has two mechanisms. One is a branch mechanism, which is similar to generating the children, and there is a bound mechanism, which just tells you to, which just gives you an upper bound using which you can terminate a branch. That's why the name of the algorithm, branch and bound, right? So consider this graph that we have on the left, right? And we want to go from A all the way to G, and we have all these nodes, right? So in how will our search tree look like? So from A we can go to B, C, and D, right? So we go to B, C, and D. B with the cost of 1, C with the cost of 3, and D with the cost of 2. From B we can go to E and H. From B we can go to E and H, each with the cost of 5 and H with the cost of 3, and so on. So which do you think is the shortest path from A to G? So can anyone comment which path is the shortest from A to G in this graph? Yes, it is A, D, F, G, right? Because 2 plus 1, 3 plus 1, 4. This is the least path. Right, you guys got it right. It is ADFG with the cost, which can also be seen from the search tree here. So if you see all the paths, so you can go either from, yeah, from A you can go to B to E, and G. So this is 1 plus 5, 6 plus 4, 10. So this is the path is 10. This path is 5. A B H G is 5. A C E G is 3 plus 4, 7 plus 4, 11. A C F G is 3 plus 3, 6 plus 1, 7. ADFG, that is 2 plus 1 plus 1, so that is 4, and that is obviously the least cost path. So how can we apply the branch and bound here? So for branch and bound you need two things. First is the branch policy, and here I just tell you to pick the lowest edge. Here I just tell you to pick the edge with the least cost, right? So how would it look like? Okay, so what is the first thing that you will do? You will pick the edge with the least cost. So from A you will go to B, and from B you will go to H, because between E and H the least cost is 3, and from H you only have one option to go to G. So this yields us to a solution path of cost 5, right? So we did find a solution with the cost of 5. So that means we have found a bound that if there is any path that is greater than 5, we can just terminate it, because it will not lead us to an optimal solution, as we have already found a goal with the solution 5, with the cost 5, right? So you can see that this path, for from going to A to, after going from A to B, you can chop this, you can branch this, you can terminate this branch, because you already paid a cost of 6, where when we only need to pay a cost of 5. Similarly, you can branch off this subtree and this subtree, and finally after doing all these branch and bound things, you will eventually end up the with with the least cost goal G, whose cost is 4, 2, 1, 1, right? But how will this progress is, first you will go from A to B to H, you will find a solution cost 5. Then the second thing that you will do is pick the second least cost edge, which is 2 here. So you will go from A to D, and from then D to F, and then F to G, and you will update your cost to 4, that you have now found a least cost goal with the cost 4. Then you backtrack from D, you can go to H, but since you have a cost of 4, you will never go to 7, and you will just not explore the tree beyond H, right? Then you have explored the entire subtree of D. Now you backtrack to A. Then you go to C. So you are paying 3. Then from C you see that okay, after exploring C, I see that the next cost is 3 plus 3 6, which is greater than 4. So I will not explore anything in the C subtree and go back to A and stop. So the least cost goal that I found was G, and the path is ADFG. So was this example clear? Okay, cool. So we can resume, and yeah. So just simply comparing depth first search branch and bound versus iterative deepening A star. So both are optimal. ID A star never expands a node with FLU greater than optimal cost, but just like its counterpart IDDFS, this is also not systematic. Mind you, systematic tells us that we have visited a node in the state space at most once, right? So depth first branch and bound is systematic, and it never expands a node twice, but it also expands a suboptimal node, right? So then you can just ask the questions that if we have a search tree of bounded depth, which one of these would you prefer? Either depth first search branch and bound or IDA star. So can anyone comment if we have a tree of if we have a search tree of bounded depth, would you prefer depth first search branch and bound or would you prefer IDA star? Hmm. And when it is easy to find a suboptimal solution, when it is easy to find suboptimal solution, and what about infinite search trees? Okay. So if you visit the lectures, you will find the answers to these questions. I encourage you to please go through the lectures once because it will also help you a lot to solve the assignments and get the certificate. So how many of you here have gone through the lecture slides before coming to this tutorial? Just show of hands. So you might already know the answers to these questions, right? Because these were already discussed in the class. Okay, cool. So now we come to the idea of admissible heuristic. So this is a very simple thing that let's say if you want to have a solution to 8 puzzle problem, right? So what can be a admissible heuristic? So you can comment if you want, if you know like what could be the admissible heuristic, or if someone might want to take a guess. Hmm. Right. So yes, it is Manhattan distance and the number of misplaced tiles. Yes. So H1n is the number of misplaced tiles, which is one heuristic to which is admissible. And why do you think it is admissible? Are you sure it will never overestimate? Okay. So let's talk about the first heuristic, which is the number of misplaced tiles. So the reason it will never overestimate is simple, that you that this that you will need to make at least those many moves to get the tiles in their correct position. So the number of misplaced tiles and total Manhattan distance, these essentially tells you the least number of moves that you will require to move a tile in its current position to take it to the goal state, right? So if I have h1 of n as the number of misplaced tiles, so can anyone tell me what is the h1 of the start state? What is the heuristic of the start state? And you are given the goal state on the right and the start state on the left. So can anyone tell me what are the h value for the start state for h1s and h2s? Okay, 8 for h1 and for h2. For h2, what about h2? And if anyone does not understand how it is how it is 8 for h1, you can just ask in the chat, like if it is not clear. Okay, so our heuristic one is the number of misplaced tiles, right? Okay, so our heuristic one is the number of misplaced tiles. So if you see in the start state, these are the 9 tiles, and not one of them is in its correct position. So 7 is not at its correct position, 2 is not at its correct position, 4 is not at its correct position, 5, 6, 8, 3, 1, none of them are at its correct position. So h1 of n is h1 of s is 8 because the number of misplaced tiles is 8. Now for h2 of n, did anyone compute the h2 of n, the total Manhattan distance? Even before that, do you know what is a Manhattan distance? How many of you does not know what is a Manhattan distance? Okay. So Manhattan distance essentially tells you, it essentially tells you how many horizontal and vertical moves you need to make to move the tile from its current location to its desired location, right? So for example, in this case, you want to move the tile number 7, right? So this is your start position, and in the goal state you want your tile state, you want your 7 tile to be here. So how many horizontal moves plus vertical moves you need to make? So it will be 1, 2 and 3. So this gives you the Manhattan distance. It can also be 1, 2 and 3 like this in the L way, or it can simply be 1, 2 and 3 in the totally vertical way. So for 7 you need the cost of 3. For 2 you just need to slide it to the right, and if you add this entire thing you will get h2 of s. So these are some examples of admissible heuristic. Now can anyone tell me, is h1 of s will be more or h2 of s will be more for any given case? For any given configuration and a goal state, will h1 of s be more or h2 of s will be more? h2 will be more, h2 will be more, h2, h2. Yes. So there is this concept which is known as dominance, and if h2 is greater than h1 for all n and both are admissible, then h2 dominates h1, and naturally h2 will be better for doing your search as it is more informed, right? So here is an example that if the depth is 12 and the iterative deepening search has 3,66,000 some nodes, 3 million nodes, whereas A star H1 just needs 227 nodes and A star H2 just needs 73 nodes. Similarly, at depth equals to 24, IDS it is just too many, whereas A star H1 only takes 39,000 nodes and A star H2 only explores 1,641 nodes. So now we can just come to some sample quiz problems, right? So the first question from me to you guys is, if H1 and H2 are two admissible heuristic, then which of the following are guaranteed to be admissible? Max of H1 H2 comma 1, min of H2 H1 H2 comma 1, square root of H1 into H2, or H1 plus H2. Which of the following? Oh, I already put the answer. Okay, don't see that, but just tell me which of the following heuristics are optimal. Can anyone comment? Is my question clear? Am I audible? Have I lost the signal again? Okay. No, no. I'm just asking you. I have not discussed. I'm just asking that if this is the if these are the options that are given to you, H1 and H2 are two admissible heuristic, then which of the following are guaranteed to be admissible? Yes, so max of H1 and H2 is guaranteed to be admissible. Min of H1 comma H2 plus 1, is it guaranteed to be admissible? No. So the answer is no, it is not guaranteed to be admissible, and it can be simply understood by a case. So let's say you are at a node which is just one step from the goal, right? So both H1 and H2 will have one, right? And indeed, the final heuristic that you should get should be 1, because that is just one step from the goal. But if you do min of h1 comma h2 plus 1, there you will get min of 1 comma 1 plus 1, which is 2. That is the heuristic for the node that is just one step from the goal. You are saying that no, it will take two steps. That means you are overestimating, which does not satisfy the criteria for admissibility, hence it will not be guaranteed to be admissible. Likewise, for h1 plus h2, similarly you can say that for h1 plus h2 also it will not be admissible. Now square root of h1 and h2, in the same case it will be 1 times 1, which is square root of 1, and it is admissible, right? So is this clear now? Okay, so for H1 plus H2, why it is not admissible is, consider, like, just go through the example that I was just talking about. So let's say you have a node which is just one step away from the goal node, right? So the heuristic of that node will be 1 for both the cases, H1 and H2, because they are admissible. Now if I add them, I will get the heuristic value of 2, but its actual heuristic value is 1, right? That means you are overestimating, which violates the condition of admissibility. Hence, h1 plus h2 cannot be the answer. And square root of h1 plus h2, okay. See, you can think of it as that. You can think of it that way. So h1n will be less than or equal to h star n, right? h2n will also be less than or equal to h star n. Now, if you multiply both of these, you will get h1 times h2 will be less than or equal to h star n the whole squared. And if you take the square root, you will get square root of h1 times h2 is less than or equal to h star n. So that thing is less than or equal to h star n. Hence it is optimal. Hence it is admissible. It is clear now? Okay, yeah, I saw your comment. Okay. So moving to the next question. Which of the following evaluation functions would estimate the behavior of a greedy best first search? So how many of you remember the greedy best first search? It was discussed in the beginning of the lecture. So greedy best first search is that pick the node that you think is most desirable, right? So which of these things do you think, which of these f values do you think will be the best estimate to the greedy best first search? And if others are not, you can also say why not. Like if you want to add your explanation for why not, you can also comment why not. Hmm. B is fine. Yeah, so the correct answers are B and D. Why not A and C? Because A is clearly an example of uniform cost search. Because f of n is g of n, that means you are picking the least cost h, right? And f of n equals h of n is, that means you are picking the most desirable thing. F of n is gn plus h of n, which gives you the equation for a star. And f of n is 2hn is also, can also be an example of greedy best first search, because there also you are considering the best desirable node. Although you have just doubled the cost, but still the order of nodes would remain the same. So 2hn can also be considered as an answer. Okay. Now, next question. Which of the following graph search algorithms are guaranteed to be complete and optimal? Just think, make sure you are saying that complete and optimal, right? And you have to assume positive edge cost. So your options are breadth first search, A star with zero heuristic, uniform cost search, and A star with admissible heuristic. Which one are guaranteed? Guaranteed to be complete and optimal. Okay, so I saw why not breadth first search? Okay, in yeah. So the options are B and C, A star with zero heuristic and and uniform cost search. Why not breadth first search? Because if your branching factor is infinity, then you might never end up finding a goal. And similarly, A star with admissible heuristic, why it is not okay, sorry, breadth first search will not be optimal. It is complete, but it might not be optimal. It is optimal only when you assume the costs are 1, when the step costs are 1. If you remember the previous slides, there I have shown you that a breadth first search is indeed complete, but it is not optimal, right? Because it can lead to suboptimal goals. A star with zero heuristic is both complete and optimal. Uniform cost search is also complete and optimal. And A star with admissible heuristic, it is it is optimal, but sometimes it might not be complete. And the case, if you remember, was if we have infinitely many nodes for which f value is same as the f value of the optimal goal, which was where, which was I think here. Uh, Yeah, which was here. So A star is complete unless there are infinitely many nodes with f less than equal to f of g, and it is optimal depending upon the search algo and heuristic property. So yes, it is optimal if heuristic is admissible, but it might still not be complete because there might be a lot of nodes which might have the optimal cost less than or equal to the goal. All right, so this is clear. Can we move to the next question? Okay, since I see no new questions, I'll just proceed. Now consider the following directed graphs having H as a starting node and G as the goal node, with H cost as mentioned, and the heuristic values are given using the following function, right? So which of the following options are correct? So you are given that from A to B the G value is 2, from A to C the G value is 3, and so on. And the H value of each of the nodes is given from the following set, that H of A is 7, H of B is 6, H of C is 5, D is 4, E is 3, F is 3, and G is 0, because that is the goal state. Now, do you think is the given heuristic admissible? Let's first comment on that. Is the given heuristic admissible? Can any one of you write in the chat? Or I can enable the mics for this particular session if you want. Okay, let me just turn on the mics. I think this needs to be a bit more interactive. Okay. Okay. Yeah, you can turn on your mics now and speak if you want to. Because this needs to be a bit more interactive. So, do you think the current heuristic is admissible?
Yes, sir.
Okay.
I can't see any unadmissible costs.
Hmm?
Although heuristic, where is the heuristic? Okay,
Heuristic is here. H of A equals to 7, H of B equals to 6, and so on. So these are the heuristic values, and this is the graph. So you have the G values here. Now is the given heuristic admissible? Okay. So let us start with. So we will start with A, right? So what is the shortest path? What is the optimal path from A to G? Can anyone shout that out?
A, D, E, G, and E, C, D, E, G. Both are optimal.
A.
A, D, E,
Hmm. A.
A, C,
Hmm.
E, G.
A, C, D, E, F, G.
No, E, G, E, G, not F, G.
A, C, D, E, G. Okay.
And A, D, E, F, G.
A, D, E, F, G. Okay. So and what is the cost of that path? That is 4 plus 1 5 plus 1 6 plus 3 9. So we are obviously underestimating at A, right? Because 7 is less than or equal to 9. So that means at A it is admissible. What about B? What is the shortest path from B to G? What about the shortest path from B to G?
It's A, D, E, B, B, D, E, G with the cost of 7, 8, sorry, cost of 8.
Ah, yeah, cost of 8 and H of B is 6. So there also we are underestimating. That is fine. For C,
With the cost of 6, C, D, E, G.
okay. So there also we are underestimating because H of C is 5. Now for D,
Cost is 5 and we are underestimating, of course.
cost of 5, yes. We are underestimating. Similarly for F, E and F, you can see that H of E is 3, which is 4 here, and H of F is 3, which is 3. So 3 is less than equal to 3. So we are underestimating. So it is admissible. Now is it consistent? What can you say about consistency?
It is consistent. Okay, so did we prove it's admissible or it's consistent?
We just proved it is admissible because at every point we are underestimating. If it is underestimating, that means it is admissible. For consistency, you need to check the triangular inequality that h of A should be less than or equal to 2 plus h of B. So for A is 7, right? So for A, you need to check all of its children. So B, h of B is 6. So 7 is less than or equal to 6 plus 2. That is true. 7 is less than or is less than equal to 4 plus 4. That is also true. and 7 is less than or equal to 3 plus 5, 8, which is also true. So for A, it is consistent. Similarly, for B, you can check for B, the only child is D. So h of B is 6 and h of D is 4. So 6 is less than equal to 3 plus 4, which is 7. That is true. So for B also it is true. For C, the only child is D. So h of C is 5, h of D is 4, right? So h of C, which is 5, is less than or equal to 4 plus 1. So that is also true. And likewise, you can check for E and E, F, and G. So and you can just let me know. So is it consistent? Did you guys check? How many of you checked? Okay.
It's consistent, sir. Checked it.
Okay. Yes. So this heuristic is consistent and admissible, right? So now, since this heuristic is admissible and consistent, what is the order of exploration of nodes using the A star algorithm? So can would anyone like to wager a guess on this before I start?
Sir, can you like expand the like? Can you pin
Yeah,
the
yeah. Sure,
slide?
sure, sure, sure. You can please draw this figure, and then I will just shift it to the shift it to my drawing board. And this will be the last question for today, I think. So we can just stop here. So can I switch now?
Yes, sir.
Okay.
Yeah, you can switch.
So Harsh is asking, can you explain the consistent part again? Okay. Harsh, so for consistency, what you need to ensure is that you need to ensure that uh, the cost that you have to reach to goal. Let's say there is a node A, and the child of node A is B. So what consistency says that h of A should never be more than the cost of generating B from A, that is C, the C of A comma B, plus the heuristic value of B. That is what the consistency constraint says. If you want, I can just show you once more in the slides for clarification. So essentially, this is what the consistency constraint says, that for every node, for every successor n dash that we can generate due to a legal action, h of n should be less than or equal to c of n comma a comma n dash, that is the cost of generating n dash from n using the action a, plus the heuristic value of n dash. So this is what is the consistency part. Okay. So now let's solve this question here, and then we will end this session. Okay. So I will just stop presenting, and I will share this tab here. Share. Okay. Cool. I hope my screen is visible. My pad, like my drawing pad is visible. Okay. Cool. So how did our graph look like? Just give me a minute. I'm just loading it here. So this is what our graph looked like, right? So we are starting from, okay, just give me a minute. Okay, so we are starting from A, right? So uh, in our frontier, in our frontier, we have A, and in this we will also have one explode set, right? So first we will pick our front, we'll pick the root node which is A and put it in explode, right? So then how will our frontier look like? So in our frontier we will now put the children of A, right? What are the child of A? The child of A are B, C and D. Now B is with the cost of 2 plus 6 which is 8, right? C is with the cost of 3 plus 5 which is 8, and D is with the cost of 4 plus 4 which is 8, right? So we'll just put in the lexicographical order since all the H values are same. So how we will do? We will do B with the cost of 8, C with the cost of 8 and D with the cost of 8, and our explode set just is A, right? Now we will pick D with the cost of 8 and we will expand it, right? So from B we can only go to D, and what is the cost of going from going like this? So it is 5 plus 4 9, right? From B we can only go to D, and its G cost is 2 plus 3 5, right? And its H value is 4, so that is 9. But we already have D with the cost of 8, so we will just ignore this and put D in the explode node, right? So what do we get? We get we get B C with the cost of 8 and D with the cost of 8. Now we will pick up C, right? So C with the cost of D, its only child is also D, right? And how do we get from there? So we will pay 3 plus 1 4 plus its heuristic cost 4 which is 8, and we already have D with the cost of 8, so we just remove this and place it here. So in our explode set we will have A, B and C, and now we will pick D for expansion, right? So what are the childs of D? For D we have E and F, right? From D we can go to E and F. So with E, it is 4 plus 1, 5. That is the cost to reach E. Plus the heuristic of E is 3. So this is 4 plus 1, 5. 5 plus 3, 8. Right? Similarly for F, this is 4 plus 2, 6. And the cost is. Oh, that was blocking. Just give me a second. Yeah. Hmm. So it is 4 plus 2, 6. And the F value of F is H value of f is 3. So this is 4 plus 2, 6, 3 and 9. So in our explode set, we will now push D. So it was A, B, C, and now we will put D. And our frontier will only have E and F. E with the cost of 8 and F with the cost of 9. So everyone is with me so far? I hope
Yes,
there is no
sir.
confusion, right?
Yes, sir.
Okay. So we are E with the cost of 8 and F with the cost of 9. Now picking the least cost, which is E, and its neighbors are F and G. The cost of F, so the F is 4 plus 1 5, 5 plus 1 6, and its own H value which is 3. So this is 9, and we already have F with the cost of 9. So we will ignore this. And for G we will have 4 plus 1 4 plus 4 8, right? And we will 4 plus 1 4 plus 8 9, and we will add this to our frontier and remove E, right? So how it will look like? So we will have F with the cost of 9 and G with the cost of 9, and in our explode set we will have A, B, C, D and A, B, C, D and E, right? Now we will pick F to explore. F F's only child is G, right? And that is G with the cost of 6. So that is 6 plus 3 plus 0, which is 9, which is already in the list. So we will just ignore this and remove F and put here, right? And finally we will pick G. We will check whether this is goal. It is indeed the goal, and hence we return. So this is what our exploration state looks like: A, B, C, D, E, F, and G. So essentially we have explored all the nodes. Is this example clear?
Yes, sir.
Okay. Mm, so then we will just do one.
Sir,
Yes.
I have problems with assignment two as well, whose answers were revealed yesterday.
Okay.
You said we will discuss them at the end of the session.
Okay. Okay. Just give me a minute because I have to check whether I have